All right, last example here. Let's take a look at section 5.3, example 1. We are going to be doing volume by cylinders now instead of washers or discs. So the idea with cylinders or cylindrical shells is that you're going to try and break up your volume into a bunch of concentric cylinders. So here's an example showing volume using cylindrical shells. So here's our curve, and we're going to rotate around the y-axis here. So if we rotate that around, then that solid's going to look like that. And we want to see what the approximating cylinders will look like, cylindrical shells. So here's an approximation with one cylinder. So not seeing a whole lot going on there, but let's say we have 3 cylinders here. So this one down here, this cylinder rotated around, and then this one rotated around. And here's with 5 cylindrical shells. So you see this inside shell, second one, third one, fourth one. Well, I guess this first one is at height 0. And here is with 10 cylindrical shells, and you can see that this is getting closer and closer on the cross section to approximating the curve. So we're adding up the volume of all of these concentric cylindrical shells, and that's going to approximate the volume of that whole solid of revolution. And now when we max this out at 15, you can see that there's even less error. So when we take an integral to add up those volumes of those shells, then we're going to get the exact volume of the solid of revolution. So now each one of these shells here has volume 2 pi r f of x dx. So if you take one of those cylindrical shells here and you cut it up the side and unravel it, so you cut it along here and you unroll that, then you are going to get a rectangle, actually a rectangular solid because it's got small thickness. And the volume of that is going to be length times width times height. So our length right here, well, that came around the circumference of that circle on the top of the cylindrical shell. So that length L is going to be 2 pi r, where r is the radius of the cylinder. And then the width right here, that's going to be your height, which is going to be your f of x, so 2 pi r h. And then your height here, that's going to be the thickness. So that's going to be our let's see, we could call that dx if we wanted to. So here, 2 pi x, x is going to be our radius because we're going to be rotating around an axis here, and then your radius is going to be an x coordinate. So your axis is down here. That radius is going to be an x coordinate. And then your height here is going to be f of x for that x coordinate. So your radius is x and your height is f of x. So this is radius and this guy is height. And then the dx is your thickness. So we want to find the volume from rotating the region bounded by y equal 1 over x. That's right here. Y equals 0, which is the x-axis. X equal 1, which would be right here. That's x equal 1, and then x equal 10, which is out here. So we're going to take and rotate this yellow region right there. It's not filling in there, but the yellow right here. So we're going to try and rotate that around the y-axis. So when we rotate that around, we're going to get another segment here on the other side of the same height. And then that's going to taper down here. I don't quite have it there. something like that. And then in the middle, see, we're taking this region here and we are rotating around the axis here. So you're going to kind of get this volcano. So here's the top of the volcano there. And then you'll have a hole at the bottom. So it's kind of a volcano with a hole in it. And then you're rotating around this guy here too, like that. So I want to try and draw a typical shell. So the radius out from the y-axis is going to be some x value. Let's put it right there. And let me draw my shell in red so it stands out. So I'm going from the x-axis up to the 1 over x function. And when I rotate around, it's going to do the same thing on the other side. And so I'm going to get something that looks like this. And it's going to have a thickness on the inside, small thickness. So that's a little shell. We're going to add those shells up starting from this shell right here, which is a radius of 1. Out to the shell at radius of 10. This is part of it right here. So our volume is going to be the integral from 1 to 10. So because we're adding up shells from radius 1 to radius 10, all these little shells. I know that looks like a washer, but it's supposed to be taller than it is thick. And 2 pi x, and then our f of x, the height here, is y equal 1 over x. Actually, at this x, the height there is 1 over x. So 2 pi x times 1 over x dx. That's our 2 pi x f of x dx. And so let's see here. The 2 pi can come outside the integral. X and 1 over x are going to cancel. This is 2 pi times the integral from 1 to 10. And all that's left in there is 1 dx. Well, that's a pretty easy integral. Antiderivative of 1 is x. So this is 2 pi. And your antiderivative is x. And we're going from 1 to 10. So plug in 10, plug in 1, and subtract. So that's going to be 2 pi. And then plug in 10 minus plug in 1. That's 9 times 2 pi, 18 pi. So that's not too bad for, really unusual shape like that. And sometimes doing the shells is easier than doing the discs. So it just depends on what you're rotating, what the equations are. So that's pretty cool.